All right, this is Tianlong Feng, z5264463. Greetings, my fellow astronomers. Are you eager to understand more about the solar system? Well, look no further. Let's jump right into Kepler's laws, the foundations of our studies of celestial mechanics. Kepler's first law, also referred to as the law of ellipsis, tells us that planets move around the sun in an elliptical orbit, with the sun located at one of the two foci of the ellipse. Right, moving on to Kepler's second law, more commonly referred to as the law of equal areas, implies that a planet orbits faster when it's closer to the sun and slower when it's further away from the sun. Kepler's third law says that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis, with the ratio of the square of the orbital period to the cube of the semi-major axis being constant for all planets. Right, now that we've got a solid grasp of what Kepler's laws are and how they work, let's apply this knowledge to a fascinating experiment. I want you to pay attention to the Earth in the simulation. Do you notice any movement? Upon initial observations, it appears that a planet stays stationary, while the moon orbits around it. However, upon closer examination, the Earth is indeed moving around the center of mass relative to a static observer. This is made even more evident as we increase the speed of the simulation. Now let's compare this to the interaction between the Earth and the Sun, which we saw in earlier parts of the experiment. There are quite a few noticeable differences here. Well, first off, the Earth is no longer the primary body, being replaced by the Sun. Furthermore, the orbital period has been greatly increased from about 27 days to roughly a year. The two orbits also have different major axes, with the average distance between the Earth and the Moon being 384,400 kilometers, while the average distance between the Sun and the Earth is 147.99 million kilometers. So another difference between this scenario and those previous is in the position of the center of mass. But before we discuss these differences, let me clarify what exactly is the center of mass. I'd like you to imagine two people of different weights on a seesaw. The center of mass is the spot where they can balance perfectly. Since the position of center of mass is proportional to the masses of the objects, and because the mass of the Earth, the Sun, is roughly 330,000 times the mass of the Earth, the center of mass is extremely close to the center of the Sun, relative to the Earth. In fact, it sits within the Sun. Doubling the mass of the Earth would cause the center of mass to creep closer towards the Earth, but this effect is still negligible with the center of mass still remaining inside the Sun. Conversely, say for example we double the mass of the Sun, we can see the center of mass moving even closer to the center of the Sun. With the grid lines turned on, each marking represents roughly 0.49 astronomical units, which also approximately equates to 73.74 million kilometers. To investigate Kepler's third law, we ran a simulation of planets of the same mass but differing distances to the Sun. We first set the planet distance to 0.73 astronomical units and adjusted the orbital velocity by shifting the velocity vector accordingly to form a circular orbit, which produced an orbital period of 219 days. We repeated this step for the planet at 1, 1.22, and 1.7 astronomical units away from the Sun, which gave us 365, 507, and 632 days respectively. Our experiment does contain a decent margin of error, which can be attributed to the fact that a lot of the measurement was done by eye. However, the results show that the ratio of orbital period squared, the semi-major axis cubed, stayed approximately constant throughout the experiment, with the largest relative approximate error being 8.78%, which supports Kepler's third law. In our experiment, we can also notice that the orbital velocity increases as the orbiting body gets closer to the primary body and vice versa. As such, the planet in our solar system expected to have the fastest orbital velocity would be Mercury, since it lies closest to our Sun, and Neptune would have the slowest velocity as it's positioned furthest away from our Sun, with the exact velocity shown in the slide. Right, to wrap up, having studied physics in high school, this experiment, and by extension this course as a whole, was a nice touch of nostalgia and revision. For using the provided stimulation and doing my own research, I've gained a greater understanding of the universe, and very much look forward to continuing my astronomy journey. Thank you, and stay curious.